All right, today we're diving into a really cool piece of engineering that tackles a huge problem. How do you grow food locally all year round, even when it's freezing outside? Let's get into it.
I mean, seriously, think about it. Can you grow fresh lettuce in a blizzard? It sounds kind of impossible, doesn't it? We usually think of winter farming as a constant battle against the cold. But what if the secret wasn't to fight nature, but to design a building that's just smarter?
And this is really where you see the two approaches clash. On one side, you've got your standard greenhouse. It just burns fuel like there's no tomorrow, which costs a fortune. On the other side, you have the deep winter greenhouse. It's designed to be smart, using passive solar, being incredibly efficient, and aiming for production 365 days a year.
So the fundamental problem is that most greenhouses are really just built for extending the seasons a little bit. The moment real winter hits, they become these energy black holes, just guzzling expensive fuel to stay above freezing. It's a completely unsustainable fight against the cold.
And that's where the deep winter greenhouse, or DWG for short, comes into the picture. It's not just a building, you see. It's an entire system. It's engineered from the ground up to work with its environment, instead of constantly fighting against it.
So let's get a clear definition here. A deep winter greenhouse is basically a passive solar machine. The whole point of its design is to do one thing really, really well: use the sun as a giant free furnace, even on the shortest, coldest days of the year. So how in the world does it do that? Well, the whole process kicks off by being incredibly clever about capturing every last ray of sunlight. And as you're about to see, it all comes down to geometry.
Okay, so check this out. These rules seem simple, but they are absolutely critical. First, you build the greenhouse on an east-west axis. That gives your longest wall, the one with all the glass, a full day of southern sun. Then, you make that wall super steep so that the low winter sun hits the glass head-on at a perfect 90-degree angle. That just maximizes the energy pouring inside.
And the smart design doesn't stop at the walls. It extends to how you lay out the plants inside. So even though the building faces east-west, the plant rows go north-south. Now, why would you do that? Well, as the sun travels across the sky, this layout means no single row of plants can cast a permanent shadow on the row behind it. Everybody gets a turn in the sun.
But, capturing heat is only half the battle. If you can't store it, it's just gone the second the sun sets. So the next piece of this brilliant puzzle is a massive, underground thermal battery.
And this secret weapon has a pretty cool name: the climate battery. It's this absolutely ingenious system that lets the greenhouse stay warm long after sunset, basically unhooking it from the daily cycle of the sun. So GAHT, which stands for ground-to-air heat transfer, is the engine that makes this climate battery run. During the day, when the air at the peak of the greenhouse is super hot, fans suck that air down and push it through pipes buried deep in the soil. The soil just soaks up all that heat. Then at night, that warmth slowly radiates back up, keeping the whole space stable without ever kicking on a furnace. And this is where the economics just become staggering. Just look at these numbers. Running a typical propane heater costs over $2 an hour. The GAHT system, it's just running a few small fans. We're talking 32 cents an hour.
I mean, this chart really puts it all into perspective. That little tiny bar on the right, that's the hourly cost of the GHT system. And that huge one next to it is the propane. The savings here aren't just a little bit. They can literally change the entire financial picture for a farm.
And if you like the hard science, here's the number to back it all up. The coefficient of performance, or COP, is just a measure of efficiency. This system has been measured with a COP of 6.81. That means for every 1 unit of electricity you put in to run the fans, you get back almost 7 units of heat from the soil. That's just insanely efficient.
Okay, so you've captured the sun's heat, and you've stored it in the ground. The final piece of this engineering puzzle is making sure that precious warmth doesn't escape. And that is all about insulation.
You're essentially building a fortress against the cold. The north wall, which never sees the sun, is insulated like a high-end house. The foundation gets wrapped in foam. They even use something called a Swedish skirt, which is a layer of insulation that goes out horizontally from the base to stop heat from escaping sideways. And of course, every single crack and leak is sealed tight. It's basically a thermos for the earth.
Now, picking the window material, the glazing, is a really big deal. Sure, cheap plastic film works, but its insulation value, that R value, is pretty low. For cold climates, the clear winner is multi-wall polycarbonate. A 16mm sheet has an R value of 3.2. That's nearly double the film, and it can last for decades. It's a key investment for the long haul.
And this quote from the source material really drives the point home. If you combine that high-performance glazing with thermal curtains, which are basically just a heavy blanket you pull over the glass at night, you can slash your heating needs by up to 60%. That is a massive, massive impact.
So, what's the result of all this careful engineering? Well, you get some incredible payoffs, and not just for the planet, but for the farmer's bottom line too.
Let's just come back to that one number for a second, 60%. That is the potential reduction in heating costs just by adding thermal curtains. It is one of the single most effective upgrades you can possibly make.
And here's the best part. Because those savings are so big, the investment pays for itself incredibly fast. We're talking a payback period of just 1 to 3 years. Everything after that is pure savings, year after year.
But the benefits really go way beyond just a lower heating bill. These kinds of systems can qualify for huge tax credits. They have way fewer moving parts than a furnace, so they last longer and cost less to maintain. And most importantly, they make year-round local food production a real possibility, which is a giant leap forward for food security.
You know, this quote just sums the whole thing up perfectly. A deep winter greenhouse isn't just a building. It is a finely tuned machine, built for one purpose: managing energy. Capturing it, storing it, and holding on to it as efficiently as humanly possible. So it really leaves you with a big question, doesn't it? As we look for more resilient, more sustainable ways to feed ourselves, could clever engineering like this be the key? Could this unlock fresh, local food for everyone, no matter what the weather's doing outside? It's a pretty powerful thought. Thanks for joining us.